Guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on General Organic Chemistry, and I hope you are enjoying this course with me. We are on to GOC Part 2, lecture number 11, but make sure you watch the previous ones before viewing this one. In GOC Part 1, we had a detailed discussion of the nomenclature of organic compounds, and Part 2, we are discussing isomerism, and in isomerism, we are discussing optical isomerism. So far, we have had two lectures on optical isomerism. Lecture number 1, we discussed what are chiral molecules, and lecture number 2, we discussed what is a chiral carbon. Now, moving further, in this lecture, well, we are going to define what is optical isomerism. Yes, we've not even defined optical isomerism, and we are on to lecture number 3. But well, we have made this course in such a way so that you understand the concepts slow and steadily, and you can remember them for a long time. So in this lecture, we are going to learn what is optical isomerism, and how are we going to learn it? Well, we are going to today study the properties of chiral molecules, and in this study, we are going to establish a relationship between chiral molecules, enantiomers, and optical isomers. And here you will be learning what is optical activity, along with learning what is optical isomerism and what are optical isomers. And in this process, well, you are going to learn a very important concept. What is plane polarized light? What is the working of a polarimeter? How does it measure the optical activity of various molecules? And a very important term is going to come in between, that is going to be specific rotation. So all this we are going to learn today. Very important concepts that you have to understand. So please be with me throughout the lecture. In fact, my suggestion to you would be, please watch the complete portion of optical isomerism. Do not miss anything, because without watching it completely, you will not be able to master the concept. We have designed the course in such a way that you can have a proper understanding of the concept, and you do not commit any mistake during the examination. So please be with me throughout the complete discussion of optical isomerism. Do not miss a single lecture. So having said that, let us begin the learning today. So let us start the learning today with the revision of two definitions that you have learned in the previous two lectures. That is, what is a chiral molecule and what are enantiomers. So molecule is going to be chiral if its two mirror image forms, they are non-superimposable in 3 dimensions, and this property of the molecules is called as chirality. And what you have learned about enantiomers, what are they? Enantiomers, they are stereoisomers. Isomers which are having same molecular formula, same structural formula, but they are differing in the spatial arrangement of atoms. So enantiomers, they are stereoisomers whose molecules, they are non-superimposable mirror images of each other, and they are going to occur only with those compounds whose molecules are chiral. So this means that if we have two chiral molecules which are non-superimposable mirror images of each other, we will be calling them as enantiomers. And hence enantiomers, they are different compounds because they are non-superimposable. Now, what we should understand is that, is this only the reason that we say that the enantiomers, they are different compounds? What about their physical and chemical properties? We have defined isomers to be having the same molecular formula but different properties, and we have learned this to be true for the structural or the constitutional isomers, and also it was true for the geometrical isomers, the cis and the trans isomers. You learned that their melting points are different, their boiling points, they are different, their solubilities, refractive indices, they are different. So the geometrical isomers, they were also stereoisomers. The enantiomers, they are also stereoisomers. So do the enantiomers also have different boiling points, melting point, refractive indices, etc.? Do they have different chemical properties? Well, the answer is going to lie in the learning of the properties of these enantiomers now. So let us learn them. So the properties of enantiomers, they are quite different from the structural isomers as well as the geometrical isomers, which you know they are diastereomers, right? So the properties of enantiomers, you will find that they have identical boiling points and melting points. For example, in the previous lectures, we have seen the example of butane 2-ol, right? So we had a compound A, we had a compound B, both were mirror images of each other and they were non-superimposable. So we called the two compounds which are having the same chemical name to butanol to be enantiomers for each other. Now those compound A and B, what we are referring over here is an R2-butanol and a S2-butanol. Why we are calling them R and S, this is something that we have to still learn. We will learn that, do not worry. But what you can understand now is that if you look at the boiling points and the melting points of these two enantiomers, which are known as 2-butanol to be having the same boiling point of 99.5 degrees Celsius, they will also be having the same melting point. Similarly, there is one compound, tartaric acid, which we are going to discuss in detail in the upcoming lectures. This tartaric acid, well, if you look at, this is a R plus and this is a minus SS. So these are the two enantiomeric forms of tartaric acid, and both of them, they have 168 to 170 degrees Celsius to be the melting point, and both of them, they have the same melting and the boiling points. Alright, so that is important how we are going to name this compound. This is something that we will be learning further. And if we have a mixture of these two, an equal mixture of both of these two, and that mixture, well, if you see the boiling point, then it is going to be varying. Why it is going to be varying, again, that we will be learning further, do not worry about. But at present, what you are learned is that enantiomers, they have identical boiling points and melting points, and also they have the same indices of refraction, same solubilities in the common solvents. Why is it so? Many of these properties for these enantiomers, they are same because both of them, they are a mirror image of each other, right? And these properties, they depend upon the magnitude of intermolecular forces of attraction. And because they are mirror images of each other, so that is not going to be different for them. The magnitude of the intermolecular forces are going to be the same for both enantiomers, and hence we see that most of the physical properties for these compounds, they are going to be similar. Similarly, if you look at the chemical reactions, they will be showing the same chemical reaction except when they react with other chiral compounds, where they will be showing some different chemical behavior. So these are also chiral molecules, and if they interact with other chiral molecules, their behavior is going to be somewhat different. Otherwise, they will be showing same chemical reactions. And for this, there is a very beautiful example that I have, which you will be always remember. And that is going to be that if you look at your teachers and your parents, both of them, right, you will find all of them to be very well mannered, asking you to be disciplined, and etc, 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 and so many things, right? Everybody tells you, your teachers also tell you, your parents also tell you. But if by chance you happen to see your parents and teachers meet their old friends, you will be finding them to be entirely a different personality. Why? Because now they have met somebody who was their very old friend. They were just similar to each other. And the moment those two similar things to similar people, well, they interacted with each other, they were entirely different naughty people, right? So that is why you just remember that the chiral compounds, when they will be seeing more of chiral compounds, they will be showing different chemical properties, but otherwise they are generally going to show the same ones. So then what is the difference in the properties of enantiomers? Well, the enantiomers, they are different in their behavior towards plane polarized light, which we will be calling in short as PPL. Now, what do we mean by plane polarized light? I will just now be telling you that. But just remember that they differ in their behavior towards this plane polarized light.
It is going to be some form of light that you can understand, right? When a beam of this plane polarized light, this passes through an enantiomer, the plane of polarization rotates, and separate enantiomers rotate the plane of this plane polarized light by equal amounts but in opposite directions. So because of their effect on the PPL, they are called as optically active compounds, and because of their different effect on PPL, both are rotating the plane of PPL in opposite directions, they are called as optical isomers. So now for the first time, we are using the word optical isomers, and let us define optical isomerism. So optical isomerism is that type of stereoisomerism in which the isomers, they are identical in molecular weight, identical in the connectivity of atoms, that is the structural formula is going to be the same, and in fact most of the physical and chemical properties, they are also same, but they differ in their behavior towards the plane polarized light. They have a different effect on the rotation of plane polarized light. They are going to rotate the plane polarized light in opposite directions. It will be an equal amount but in opposite directions. What is all this going to mean? We are going to discuss that in this lecture, but just for an introduction, this is what you have to remember, right? So this is also called as enantiomerism because it is the property of the enantiomers. So enantiomers, they are themselves called as optical isomers. So now can we correlate our whole study with butane 2-ol, because this is our favorite example. We have been learning about this from so long. All the 2 lectures we have been discussing this. So butane 2-ol, you all know this is a chiral molecule. Why is it a chiral molecule? This is a chiral molecule because it is non-superimposable on its mirror image. And how do we test for that? Apart from the models and all, now we know the easy way out, that we just find out the number of asymmetric carbons, the carbon which is forming 4 single covalent bonds with 4 different groups of atoms is called as a asymmetric carbon. This carbon is sp3 hybridized. It has a tetrahedral arrangement of the atoms surrounding it, and so you all know this, that this compound butane 2-ol, it has one asymmetric carbon. And when we have one asymmetric carbon, it is 100% guarantee that a molecule is going to be chiral, right? So we know that butane 2-ol is a chiral molecule. Now when we have a chiral molecule, this means that in nature there is a possibility that if this butane 2-ol goes with a mirror and tries to search for somebody who is a mirror image of it, it may find that, right? So what did he find with the mirror? Well, he found that there was another compound which was having the same molecular formula, the same uh, structural formula, but they were differing in the spatial arrangement of atoms. They were the mirror images of each other, and then they tried to superimpose each other on themselves, and they found that they were non-superimposable. And hence these two compounds, they came to be known as enantiomers. And now we know that these enantiomers, they are called as optical isomers. Why are they called as optical isomers? They are called as optical isomers because they have a capability to rotate the plane of the PPL, plane polarized light, by an equal amount in opposite directions, right? So the chiral molecules, they have a property of optical activity. That means they can rotate the plane of plane polarized light, and the optical isomers, they rotate it in equal amount by opposite directions, right? So I hope now this whole study, this has become interesting to you, that all that we have learning, that this is the enantiomer of this and this will be the enantiomer of this. If we just simply draw the mirror image of it, which is non superimposable, well, now you know that these are the ones which we call as optical isomers. So a pair of enantiomers, they are called as optical isomers. So now with this understanding, we will move further in this course about optical isomerism. All that are enantiomers, are going to be optical isomers to each other. So this compound and this compound both having the same molecular formula, same structural formula, butane to all, these are optical isomers, right? So they are optical isomers of each other. And now what is left to learn? Well, we are going to learn what is this plane polarized light and the related learning that we have to do to understand the concept completely. So the chiral molecules, they have a property of optical activity, or we can say that the chiral molecules, they are going to be optically active molecules, or the chiral compounds, they are going to be optically active compounds. Now this optical activity, this was first of all studied by a French physicist, Jean-Baptiste Bayet, in the year 1815, and optical activity is defined as the ability of a chiral substance to rotate the plane of plane polarized light, and this is measured using an instrument called as a polarimeter. So what we have to learn is what is this plane polarized light, what is this polarimeter, and how does this help in measuring optical activity of various substances. So first of all, let us understand what is this plane polarized light, and for this first of all you have to understand what is normal or ordinary light. So normal light, this consists of electromagnetic waves that oscillate in all directions. So I hope you all remember while we were studying atomic structure, we said that light is an electromagnetic radiation. So light, this consists of electromagnetic waves. It does not need a medium to travel. It can travel in vacuum and it travels like an electromagnetic wave. And an electromagnetic wave, how does this travel? Well, it is going to be consisting of two oscillating fields, the electric field and the magnetic field, perpendicular to each other, and the direction of the propagation of light, or the direction of the propagation of the EM wave, this is going to be perpendicular to both of these. Alright. So from one point to another, light is going to travel through the oscillations in this electric field and the magnetic field, which are mutually perpendicular to each other. Now, this light, if for example you take the example of sunlight, you take the example of an ordinary bulb, what we see is that ordinary light or sunlight, this travels in all directions. It is not that you are just seeing one beam of light coming, the light is spreading in all directions. So this, if we stand at, for example, one point, and if we could see the electric field oscillations, we would find that these oscillations, they are going to be in all directions, and the magnetic field, this is going to be perpendicular to the oscillation of the electric field, and the normal light, this is propagating perpendicular to these both fields. Alright, so we can say that the electric field, this is oscillating in all directions. Perpendicular to that, the magnetic field is oscillating in all directions, and perpendicular to both of these, the light is traveling in all directions. Fine. So this is if you see it standing at this point, and if you could see all these oscillations. Now what is plane polarized light? So plane polarized light, or simply polarized light, in contrast, oscillates only in a single plane passing through the path of propagation. So if you compare it with ordinary light, you see ordinary light traveling in all directions, whereas plane polarized light, this will be traveling in only one direction. It can be any horizontal, vertical, diagonal, whatever you may choose from these, but it is going to be only one direction. Alright, so it is oscillating only in a single plane, that is being called as plane polarized light. So now the normal light, this consists of electromagnetic waves that oscillate in all directions, whereas plane polarized light, this is going to consist of oscillations in a single plane only. Now the other thing that you have to remember is that the normal light, this is going to consist of electromagnetic waves of varying wavelength. There are going to be many wavelengths which are present. For example, if we talk about the visible light, you all know Wimp and
all violet, indigo, blue, everything, they are all lights, they are having a specific wavelength, a different wavelength, and light is consisting of electromagnetic waves of all these varying wavelengths. Similarly, now if you have a plain polarized light which we have obtained from normal light, it will be consisting of electromagnetic waves of varying wavelengths. It is also going to be polychromatic. Many wavelengths are going to be present, but they will be oscillating in a single plane only. But for measuring optical activity, we require light that is of a single wavelength and is plane polarized also. Okay, for measuring optical activity, we require light which is going to consist of a single wavelength and is plane polarized also. So to have a single wavelength light, the normal wavelength that we use is 589 nanometer, that is the D line, which is corresponding to the yellow light produced by a sodium lamp. And a sodium lamp, this is like any other lamp, and its light is unpolarized, which is traveling in all directions, right? The plane of its electric field vector can have any orientation along the line of travel. So it is going to be a single wavelength line, monochromatic light, whereas ordinary light, this is going to be polychromatic. So we will be using monochromatic light for measuring optical activity, and then we are going to make this unpolarized light into a plane polarized light. How are we going to do that? Let us learn that. So a beam of unpolarized light, this is transformed to a plane polarized light by passing it through a polarizing filter, which can be a polarized lens or it can be a Nicol prism. So it is a prism, so it is going to be a doubly refracting object and it is composed of crystalline calcium carbonate. Now what does a filter do? Well, a filter, for example, we have a filter paper and we want to filter some sand water through it. What will happen? The sand will be left behind on the filter paper and the water will pass through and we will be getting clean water. So similarly, now we have a polarizing filter. What does this polarizing filter do? Well, it is going to remove all the waves except those have their electric field in the same plane. So out of the unpolarized light which has electric field in every direction, in every plane, well, we will now be having plane polarized light which is going to be having electric field vector in one plane only. Alright, and the instrument which can be helpful for us using this principle to measure optical activity, well, that is called as a polarimeter. Right? So what is polarimeter going to do? Well, it is going to measure the optical activity of a substance. How is it going to do? Well, it is going to measure the degree of rotation of the plane of polarization, and this is what we have to now understand, what is the working of a polarimeter. So in a polarimeter, what you will be seeing is that first of all, we have a light source. I just briefly tell you and then we will talk about one of them, each one of them in detail. So we have a light source. A light source is going to give us unpolarized light. We will be passing it through a polarizer, which can be a polarized lens, or generally in this polarimeter, it is a Nicol prism. Then when it is going to pass through that Nicol prism, what we will be getting is plane polarized light, line only in one plane. And then we will be passing it through the substance which we want to examine, whether it is optically active or not. And then whatever light is coming out of it, we are going to analyze this in an analyzer. Okay, so let us study one by one what all these components they are going to do to tell us about the optical activity of a substance. So first of all, we have a light source in the polarimeter and we all know about the light source. How should it be? Well, it should produce monochromatic light, that is light of a single wavelength. We do not use ordinary light because that is polychromatic. Wavelengths of many types are present in the ordinary light. So most polarimeters, they use light from a sodium are called as the sodium D-line wavelength. This I have already told you. So now this light, this is a monochromatic light, but this is unpolarized light. It has electric field vectors in all the planes. What do we require? We require plane polarized light which should have electric field vector only in one plane. So we will be passing this unpolarized light through a polarizer, which is generally going to be a nickel prism for a polarimeter. And then when we are going to pass it through, what we will be getting is plane polarized light, electric field vector of this light only in one plane, right? So next what we will be doing? Well, we will be passing this plane polarized light through an empty sample tube. So this is a tube in which we are going to place our compound, okay, to check its optical activity. But first of all, before we keep that compound in the sample tube, what we will be doing is we will be keeping it empty, or what we can do is we can have an optically inactive solvent in this. So what you require for the sample, I'll just now mention that also to you, that the sample that we are having, it should be a liquid. If it is a liquid itself, so far no problems. But if it is not a liquid, well, to check that it is optically active or not, we have to make a solution of it. And the solvent, this should be optically inactive. Okay. So what are we going to do? Well, we are going to pass this plane polarized light through an empty sample tube or one with an optically inactive solvent, and when the light is going to come out of this, it is going to be unchanged, right? Because here we have either a solvent which was optically inactive or it is empty, so it is going to come unchanged. And then we are going to pass this light through an analyzer. An analyzer is a second polarizer mounted on an eyepiece with a dial marked in degrees. Okay, so a polarizer which we will be able to see the light passing through this polarizer, and then it is also going to be marked in degrees to check the degree of rotation of light if that happens. So now when you are looking through the eyepiece, the light coming out from the analyzer, you may or may not be able to see light. If you are able to see light, what it is going to be meaning is that the orientation of the two, the polarizer and the analyzer, they are the same. And that is why the plane polarized light which was traveling in one direction, this could come out. Alright, and you could see that. What we are going to do is that we are going to rotate the eyepiece till the through the analyzer there is no light coming. We have total darkness. We cannot see any light coming. Alright. So what are we going to do? When using a polarimeter, the analyzer is rotated until the user's eye sees total darkness. So what are we going to do? For example, if the direction of this polarizer is vertical, what we will be doing is we will be having the direction of the analyzer horizontal 90 degree to it, so that no light passes through and we see complete darkness. At this point, the analyzer is at a right angle to the first polarizer so that no light passes through. This analyzer setting corresponds to 0 rotation. Alright. The next, the sample to be measured is then placed in the sample tube. So first of all, you are going to make the setting when you can see no light passing through the polarimeter. And then after that we have done it, well, we will be putting our sample in this sample tube. And this substance I have already told you that should be in the liquid phase, or it should be in a solution of a suitable solvent, and for this generally we use water, ethanol or chloroform. So now you have placed your sample in the sample tube and you are checking it through the analyzer. And if you check through the analyzer and you see complete darkness, right? What would that mean? It would mean that the plane polarized light has not been rotated. It is coming in the same direction as it was. Therefore, the sample, this is optically inactive as it does not rotate the plane of polarization. Similarly, if you change the analyzer again back by an angle of 90 degree, at that time both the analyzer and the polarizer, they will be in the same direction
and the plane polarized light, as it is passing through the polarizer, it will be passing through the analyzer, and you will be able to see that bright light which you could see earlier without the sample also. Alright, what does this mean? This means that the sample is optically inactive. It has not rotated the plane of polarization, and it is an achiral compound which does not rotate the plane of polarization because it is optically inactive. Alright, so here you will be having an achiral compound if the direction of the plane polarized light through the polarizer and the analyzer, they are going to remain the same. There will be no rotation. So now the other possibility is that the compound is optically active. The compound is a chiral compound. And when it is going to be a chiral compound or it is going to be an optically active compound, you know that it is going to rotate the plane of the plane polarized light, as you can see in the diagram also. Now it is not parallel. It has rotated by some angle, right? So if the sample is optically active, it is a chiral compound, it will rotate the plane of polarization. The analyzer will no longer block all the light, so there is going to be some light reaching the user's eye. There will be not complete darkness. Some light is going to come out. The user will then have to rotate the analyzer again until no light passes through. Alright, so you will have to rotate it. It is here, you will have to rotate it by some angle so that there is now again complete darkness. And the degree to which the analyzer is rotated can be read from the dial, and this represents the difference between an optically inactive sample and the optically active sample. There was no rotation of the plane polarized light when we had an optically inactive substance, but in an optically active substance you have to rotate it to get back the complete darkness, and this angle through which we have rotated it back to get a complete darkness is called as the observed rotation, or alpha, which we measure in degrees. So from this discussion, what we can conclude is that if the compound is optically active, it will rotate the plane of polarization. And as a chiral compound rotates the plane of polarization, it is optically active. Now for a chiral compound, there are two possibilities. One is to rotate the plane of polarization in the clockwise direction, and the other is to rotate it in the anti-clockwise direction, right? So a chiral compound is either going to rotate the plane of polarization clockwise, or it is going to rotate it counterclockwise or anti-clockwise. If one enantiomer rotates the plane of polarization clockwise, its mirror image will rotate the plane of polarization exactly the same amount counterclockwise, right? So the two enantiomers which are possible for one chiral compound, they are going to rotate the plane of polarization in the same amount but in different directions, and that is why we call them as optical isomers. I hope now this is clear to you. Now, if a compound is optically active and it rotates the plane of polarization clockwise, we will be calling that compound to be dextrorotatory, for which we will be using the symbol plus inside the parenthesis to tell that it is a dextrorotatory compound. Why do we call it dextrorotatory? Dextro, this is a Latin prefix for to the right. So, rotation to the right. Next, we have an optically active compound which rotates the plane of polarization counterclockwise. We will be calling this compound to be levorotatory. The symbol that we will be using is a minus sign inside the parenthesis. And why do we use levo? Well, it is again a Latin prefix for to the left. So, left rotation is levorotatory and right rotation is dextrorotatory. Alright, I hope you will remember this. It is very easy to remember also. Levo is also starting with L and the left is also starting with L. So left means levo and obviously right is going to be dextro. And in sometimes instead of the plus and the minus symbols, we also use the lowercase d and L to tell whether the compound is dextrorotatory or levorotatory. Now, one very important thing that you should remember is that the plus and the minus symbols, they are used to indicate the direction in which the optically active compound rotates the plane of polarization, whereas R and S, where did you see this? While I was talking about the properties of the enantiomers, they were written R2-butanol and S2-butanol. I hope you all remember. So that R and S, this indicates the arrangement of the groups about an asymmetric carbon. So about an asymmetric carbon, we have 4 groups. How they are arranged, this is what we will be understanding in the nomenclature, where we have the R and S system of nomenclature. This is something that we will be studying a bit later. So this is something that will be related to the arrangement of the groups about an asymmetric carbon. The plus and the minus sign, they have nothing to do with R and S. Alright, a R compound can be both plus and minus. A S compound can be both plus and minus. R compound can be again rotating the plane of polarization in the clockwise direction or in the anti-clockwise direction. Similarly, an S will also. This is something that we will be talking about later, so you will understand that better at that time. So now this is 2-butanol and this is its mirror image. Again 2-butanol, both are chiral compounds, both are enantiomers of each other, and both are optical isomers for each other. Why they are optical isomers? Because they rotate the plane of polarization differently. Now I hope you understand. One is going to rotate the plane of polarization in the clockwise direction and one is going to rotate the plane of polarization in the anti-clockwise direction. But you do not know which one is going to do that unless you put them in the polarimeter. Okay, so once you put this compound in the polarimeter, you will be able to find whether it is rotating the plane polarized light in the clockwise direction or in the anti-clockwise direction. So supposedly it is rotating it in the clockwise direction, so we will be denoting it by a plus sign. And if it is going to rotate, obviously the other one is going to rotate it in the anti-clockwise direction. Okay, and if this is rotating it in the anti-clockwise direction, we will be denoting it by a minus sign, and this we will be denoting by a plus sign, because both of them, they are going to rotate the plane polarized light in the opposite direction but by an equal amount. The angle is going to remain the same for both of them. Okay, similarly, let us see one more example, and this is bromochlorofluoromethane. Again, the structures you have seen in the last lecture, that is why I picked them up only. So here also, if one of them is going to rotate it in the clockwise direction, we will be symbolizing it by plus, and the other is going to rotate it in the anti-clockwise direction. If this is rotating it in the anti-clockwise direction, this is going to be rotating in the clockwise direction, but the angle for both of them, this is going to remain the same. So this is something that you have to remember very well. The only way we can tell whether a compound is dextro-rotatory or levorotatory is to put the compound in a polarimeter. It is only then you will come to know it is dextro-rotatory or levorotatory. No other way to find that out. Okay, just looking at the substances, you cannot say that it is going to be dextro-rotatory or levorotatory. Perfectly fine. I'm good. So let us now recap the whole thing that we have learned with the help of these diagrams, so that the understanding this becomes crystal clear and you remember it always. So first of all, we have the unpolarized light. We pass it through the polarizer. What we get is plain polarized light. Okay. After this, what do we have between the polarizer? If this is the polarizer and this is the analyzer, in between the two, what is missing in the diagram is the tube in which we are going to place the substance which we have to examine. Before we place that substance, what do we first of all place? We place the tube only with the solvent. For example, we place it with water. Okay, and water, this is going to be optically inactive. And when the light is going to pass through this solvent, the light which is going to come out, because it is optically inactive, is going to be the same plain polarized light. And when we pass it through the analyzer, well, this analyzer, first of all, you can see that this is parallel to the polarizer.
The slits in this, they are just like that in the polarizer in the vertical fashion. So if the polarizer is allowing these vertical lines to come out, the analyzer will also allow these vertical lines to come out. Okay, so the polarizer and analyzer, they are parallel to one another. There is no optically active compound present. It is only the solvent which is present, first condition. Okay, before we even start checking the compound, for which we have to determine the optical activity. And what we see is complete bright light. Whatever light was coming out through the polarizer, it is also coming out through the analyzer. So what we call it, this we call it as bright light. Okay, bright light. The next we have the polarizer and the analyzer now perpendicular to each other. When they are perpendicular to each other, just consider that this is the test tube which contains the solvent. Okay, so when the light is going to pass, it is going to be again the same way. There is going to be no rotation. But now in front of this, these are vertical slits. No, these are horizontal slits. So these horizontal slits, they are not allowing the vertical lines to pass. So what are you going to get? You will get no light. It is going to be complete darkness. Okay, so this will be your setting with the solvent. The setting with the solvent where there is complete darkness, this you are going to set the angle of your eyepiece at 0° rotation. So here you have no rotation. Okay, this is you have labeled as 0°. To check whether this is right, what you can do is rotate it by at an angle of 90°. You should be getting complete brightness. Okay, if you get this means that you have set the rotation right for complete darkness to be 0°. Okay, now once you have your eyepiece set at this point at 0°, complete darkness, you cannot see anything. Now you are going to replace the solvent by the compound which you want to check the optically active optical activity. First we have a compound which is optically inactive. How do we come to know that the compound is optically inactive? Again, because when we placed the compound, what we found was that we did not have to change the rotation and there was still complete darkness. Okay, so you change the solvent with an optically inactive compound. The rotation you did not have to do anything, and you found that as dark it was before, it is also the same dark. And if you rotate it back by an angle of 90°, you are going to again see that we have complete darkness. And in this case, now we have the optically inactive compound. Okay, so optically inactive, or there is a solvent present, it is going to be one and the same thing. Now in case we have a optically active substance, so what is the optically active substance going to do? Well, it has molecules of the compound which are going to rotate the plane of this plane polarized light. So when it is going to pass through one molecule, it is going to have a slight rotation. It is going to pass through another molecule, still slight rotation, another molecule, still slight rotation. So as it is going to pass through the length of this tube, you will be seeing that the molecule, the light, this has rotated by some angle. Okay, how did you come to know that it has rotated by some angle? Because what you were seeing was complete darkness before when you had the solvent. So when you had the solvent, it was complete darkness. But when you replace the solvent by the optically active compound, you could see some light. The analyzer now, because the light is at some other direction. Okay, so there is some light going to pass through the analyzer and you will not see complete darkness. That is how you come to know that it is an optically active compound. And then you have to measure how much is that optical activity. So you will again rotate the eyepiece so that from this lightness you again get darkness, and the rotation that you will be measuring, that is going to be the observed angle of rotation. And for this example in this diagram, what you can see is that we have rotated the eyepiece by an angle of 40° towards the left. If you rotate it towards the right, it would be dextro-rotatory, but now it is rotated to the left, so the compound is levo-rotated. Okay, so this is how you measure the angle. This is the observed angle of rotation that we have measured.
Now there is one more thing which I want you to know, and that is, in some of the books what you will be finding is that instead of darkness, the 0 degree angle is taken at complete brightness. So you can do that also. Okay, so for that what you will be doing is, only difference is that when you have set the 0 degree at complete brightness, just let me clear this out. So your 0 degree is when you have complete brightness. And when this has rotated by some plane, how are you going to check? You are going to rotate the eyepiece in such a way that you get complete brightness once again. Okay. When you are checking it at darkness, get darkness back again. When you have 0 degree at complete brightness, rotate it to get brightness once again. That is the only difference. When you take this as the 0 degree or you take this as the 0 degree, you can take both. Okay, so do not get confused on reading the book when one is saying that set 0 degree as complete brightness and the other says set 0 degree at complete darkness. So when you are rotating, you should be rotating it according to what was your base that you had chosen. Okay. So now you know that a substance, if it rotates the plane polarized light, well, it is going to be optically active, and we can also measure the angle by which it is going to rotate the plane polarized light, which we denote it by alpha. Right? I hope this is clear. Now my next question is that if we have two substances, substance A and substance B, how are we going to compare their optical activity? Both of them, they are optically active. Which one is more active? How do we compare that? Well, I know you people are very intelligent and you are going to tell me that for which compound the alpha is going to be more, that is going to rotate the plane polarized light more, so that is going to be more optically active also. But supposedly I tell you that the compound A, this is rotating it by an angle of 40 degree, and a compound B, this is rotating it at an angle of 50 degree. Okay, and you say that compound B is more optically active. But now what I tell you is that I have done another experiment, and the other experiment I found is that this is rotating it by 50 degree and this is also rotating it by 50 degree. Now what will happen? And if there is another experiment I have done, it is rotating it by 60 degree and this is still rotating it by 50 degree. What am I doing over here to this compound A? That the angle of rotation is increasing, and what is I am not doing to B, that the angle of rotation, this has not changed. Well, what I can do is I can change the angle of rotation by changing certain parameters. What are those certain parameters? For example, I just now told you that if we are going to pass this light through the sample, when it is going to reach up to one molecule, it is going to bend slightly. Reaching up to another molecule, it is going to blend more. More molecules, more is going to be the bending, right? So if I, for compound A, take some concentration X, and then I double that concentration, and then I triple that concentration, obviously more is going to be the number of molecules now in the sample tube, and more is going to be the rotation, and here I have just not changed the concentration. Alright, so if I do not specify to you what is the concentration, how will you be able to compare them? You can compare them only when the concentration in which you are taking substance A is equal to the concentration of substance B, then only you can compare. Otherwise you are going to say that, well, if this is the concentration, I did not specify you, but this is the concentration where it is 3x, and here the concentration for substance B is x. I did not specify you, and you said that A is more optically active than B, but in actual B is more optically active than A. So what do you need to know? What you need to know is that this angle of rotation, this depends on what all factors, and all those factors you should keep them constant when you are comparing two substances rotation to see which is more optically active. So the observed rotation, this is going to depend upon the number of optically active molecules the light encounters in the sample, which is going to depend upon the concentration of the sample, because more is going to be the concentration, more is going to be the number of molecules that light is going to encounter, more is going to be the bending. Similarly, another factor on which this number light is going to depend upon is the length of the sample tube. If the length is going to be more, it is having more chances to interact with more molecules. If the length would have been short, for example, if this would have been short, it would have met with only 3 molecules, but when the length is this big, it is encountering 6 molecules, as you can see. Okay, so the length of the sample tube, this is also very important, that this should also be kept constant, and the concentration of the samples, this also you should keep the same while you are comparing the compounds for their optical activity. Another thing that is going to affect this observed rotation is the temperature. All right, so on the temperature, you all know that the system's energy depends. So the molecules, their vibration and everything depends. So the temperature of the system, this should also remain constant. And the other thing that should remain constant is the wavelength of the light source, because it is the light which is traversing. So the wavelength of that light is also very important. Alright, so what are you going to keep constant when you are going to compare the optical activity of the substances? The concentration of the sample, the length of the sample tube, the temperature and the wavelength of light. So now that you know that the observed value of the angle of rotation, this can vary with certain factors, we are going to introduce another term, that is specific rotation, which is going to take care of all these variable factors. Okay, the specific rotation is going to be specific characteristic for each optically active compound. And what is the specific rotation? Well, it is defined as the number of degrees of rotation caused by a solution of 1 gram of the compound per ml of the solution in a sample tube of 1 decimeter long at a specified temperature and wavelength. Okay, so this would be your observed angle of rotation. Then the compound that you will be taking in the sample test tube, that has to be 1 gram per ml of the solution. So the concentration is also specified, 1 gram per ml, and also the length of the tube, this has been specified, that take it to be 1 decimeter cube, and the temperature and the wavelength also you have to specify when you are doing this experiment to find the angle of rotation. So this would be specific rotation. So the specific rotation, we also have a formula for that. If you are taking different concentrations and different tube lengths, and therefore the formula is alpha uh, T lambda, which is specifying the temperature and the wavelength of light used. This will be equal to alpha. This alpha is the observed angle of rotation divided by the length of the tube divided by the concentration of the solution. Alright. Now alpha, this is the specific rotation, the dark one. Alright. So alpha is the specific rotation, this one in the parenthesis. T is the temperature in Celsius. Generally we take it at 25 degrees Celsius. That is the room temperature. Lambda is the wavelength of the incident light. Generally when sodium D line is used, it is indicated as D. And the small alpha, well, this is the observed angle of rotation. L is the length of the sample tube, but you have to take always this length in decimeters. Okay, it will not be in meters, it will not be in centimeters. You have to specify the length in decimeters, and the concentration of the sample, it has to be grams per ml of the solution. Okay, so when you do this, what you will be getting is specific rotation. And then when you have specific rotation for two compounds, you can compare both of them. Okay. So now we have one example where I am going to give you all the values so that you can understand everything, and this would be the end of our today's lecture. So one enantiomer of 2-methyl 1-butanol, this has a specific rotation of plus 5.75 degrees. So when you will draw the structure for this, you will be finding that there is going to be one chiral carbon in the compound, And when there is one chiral carbon in the compound is going to be optically active for sure, 100% guarantee. Okay, and when you place this in the polarimeter, what you find is that the rotation is plus 5.75 degree. So what this means is this enantiomer, whatever enantiomer you placed for this chiral compound, this is rotating the plane polarized light by an angle of 5.75 degrees towards the clockwise direction. Okay. And what about the other enantiomer? The other enantiomer, which is going to be its mirror image, is also going to rotate the plane of polarization by the same amount but in the opposite direction. Therefore, the specific rotation of the other enantiomer is going to be minus 5.75 degrees. Okay. Both of them, they will be having the same value, only differentiating is going to be the plus and the minus sign. One is rotating the plane polarized light in the clockwise direction, the other is rotating it in the anti-clockwise direction. And this is how you're going to represent everything. Okay, so this is the compound. Here you can see this carbon is going to be chiral, surrounded by 4 different groups. This is its mirror image. This is R, this is S. This is something that we still have to learn, which we call as R, which we call as S. But for both of them, what you can see is this is going to be plus, this is dextro-rotatory, this is levo-rotatory. How did you find out that this is dextro-levo-rotatory? This you found out only by putting it in the polarimeter. There is no other way to find it out. The R and the S we will be able to tell by looking at the structure, but it is dextro-rotatory or levo-rotatory you will be able to find out only when the compound is put in the polarimeter. The children do make a mistake over here. Okay, so just remember this, dextro or levo is going to depend upon your experiments only. When you have put it in the polarimeter, you found it to be rotating the light, plane polarized light in the clockwise direction, you will be calling that dextro-rotatory and the other to be levo-rotatory. So here you can see the specific rotation, also the notation, 20 degrees Celsius is the temperature. The light that you have used is D line of sodium, and the angle of rotation, this is plus 5.75 dextro-rotatory and this is minus 5.75, so this is levo-rotatory. So I hope now the concept, this is clear to you. And in the next lecture, what are we going to do? Well, we will be carrying on that if our molecule is not going to have just one chiral carbon, more than one chiral carbon or no chiral carbon, then how are you going to tell whether the compound is going to be optically active or not? Okay, so that is what will be the topic of our next discussion. So that would be all for this lecture. I hope you've enjoyed this lecture with me and you are going to be with me for the next lecture. We are going to continue the discussion on optical isomerism. My only request, please do be with me throughout the whole discussion so that you have a thorough understanding of the concept. And if you're liking these lectures, one more request, well, please do subscribe, like and share with your friends also. Thank you and have a nice day. God bless you.